We're going to be studying chemical kinetics in our first unit. And in this unit, we're going to be really interested in how fast is a chemical reaction taking place. Is it really rapid and it happens in a blink of an eye? Is it very slow and it would take 1,000 years? So we are just embarking on how you monitor that. How do you know the rate at which a reaction takes place? Well, it's easy to monitor it for a car. You can measure how far it travels in a certain amount of time. So we could say that a car travels at 200 miles per hour here in the United States. You would have a different value in kilometers per hour. Or we could say, this is a really slow vehicle and it doesn't travel near that fast by measuring how far it travels in a certain amount of time. Our first learning objective is to describe this concept of rate of a reaction. And this concept of chemical kinetics and rate is defined by the change in concentration as a function of time. And we usually monitor that concentration in units of molarity, and the time might be a second interval, and that's what we'll usually use in this lesson. It could be in minutes, it could be in hours, it could be in years for that matter. But you can either watch a reactant and see that its concentration is decreasing as time goes by, or you can monitor a product and see how its concentration is increasing as time goes by. Let's look at this schematic of a chemical reaction. The reaction we're going to look at is A plus B going to the product C, and we see the colors there represented. A is blue, B is red, and C is purple. So I want you to look at the reactant A and what is happening to it as time goes by. Now we see that we've got a schematic 15 minutes, 30 minutes, 45 minutes going by as this reaction proceeds. Well, it is certainly decreasing as time goes by. We're using it up. Now we want to be able to monitor that and define the rate of the reaction by monitoring that. So let's think about the change in its concentration. Would the change in concentration be positive or negative? Now remember, a change, which is represented with delta, is always final minus initial. So if you think about how much you have at the end versus how much you have at the beginning, would this be positive or would this be negative? Well, if you said it would be negative, you'd be correct. Now, as we continue to think about this reaction, A plus B going to C, the concentration is decreasing, the change in concentration is negative, and when we talk about the rate of a reaction, we do not say that a reaction is going at a negative rate of speed. So we have to take into account that there is a minus sign with that. This portion that we just looked at is negative. You just said that in the previous slide. And this portion here has to be positive. So if the rate of the reaction is always defined as a positive speed, we place this minus sign in there. A negative times a negative is a positive. And this way, the rate of the reaction will always be positive. Now you can't travel in a car at a negative rate of speed. You can go 100 miles an hour, you can go 15 miles an hour, you can go 47 kilometers an hour, but you can't go a negative 47 kilometers per hour. You might go backwards, but you're still going backwards at a positive rate of speed. So we have to place that minus sign in there for monitoring reactants to obtain a rate of the reaction. Now let's look at C. C is our product. What's happening to it as time goes by? Well, it is increasing. We're getting more and more of it. So if we're monitoring the rate of the reaction in terms of this C, we are not going to have that negative sign in there. We can just do change in concentration of C with respect to time. No negative sign is needed. Okay, now I've got two different reactions. The one we've been looking at, A plus B going to C, and D plus E going to F. Now I want you to look at these images and I want you to tell me which one of those reactions is faster. Well, if you said that number one was faster, you'd be correct. What we need to do is we need to watch a reactant or a product as time goes by in those two reactions, and we will see that we are using up the reactant A which was blue, or the reactant D, which is yellow, we're using up the reactant A more rapidly than D is disappearing. Therefore, A has got a faster rate of speed. All right, let's look at this graph. We're monitoring a very basic reaction. A is turning into B. A is represented with the black, so it is decreasing as time goes by. B is represented with the red, and it is increasing as time goes by. My question for you is this: is the rate of the reaction a constant during the course of the reaction? Is it running at the exact same rate of speed? Is the change in concentration over the same time interval the same? Well, it's not. If it were, it'd be a nice linear graph, but it is dropping off. If we look at this time interval of, let's say, from 5 to 10 seconds, we see that we are increasing B by this amount. This is the same time interval. It is a 5-second time interval from here to here, but its change in concentration is much, much smaller. So we have got a smaller rate of speed as time goes by. So we have to do calculations over a certain rate, and we'd have to define what that time interval is. And it's going to be different depending upon which time interval we choose as a reaction takes place. And when you're comparing reactions, you would want to be monitoring it during the same time interval to say that this one is faster or this one is slower. Now if we make that time interval smaller and smaller, eventually it gets so small that it's a point in time, and it would be an instantaneous time. An instantaneous rate could be obtained at that. Now, if we think about this in terms of a car traveling, if you're going down the road, let's say you're traveling for a couple hours, and you measure the distance that you traveled in those 2 hours, and let's say that you find that you went 140 miles in that 2 hours of time. You could say that over those 2 hours you traveled at 70 miles per hour. Well, here in the United States, that is a typical speed for an interstate travel, and that's not going too fast. But let's say you're traveling down the interstate and an officer clocks you going 100 miles an hour in that instance. Now that's an instantaneous rate, and you can't argue to the officer that over the 2 hours you're traveling, you're only traveling 70 miles an hour, therefore you shouldn't get a ticket. He knows that at that instant you're going too fast. So we can monitor a rate of a reaction over a time interval or at an instant in time. Now here is a graph that is showing that the rate is decreasing for a reactant. That's what's being monitored here. They're monitoring reactant A as time is going by. And at this point in time, the way you get that rate is to measure the slope of the tangent line. So this little red line here is its tangent line, and if we do the change in y over the change in x, we can determine the rate at that instant in time. Okay, so that's the slope of the tangent line. It gives you the instantaneous rate, and again we will see that these are not the same value. As time is going by, the rate is decreasing, but we have a value at that instant in time. Now here we have a reaction which involves gases, and you can monitor the change in the pressure as time goes by. And again, I've got a slope of the tangent line here that I could determine its instantaneous pressure change as time goes by. All right, so rates can be defined in terms of change of pressure as well as change in concentration. Now, this is using PV equals nRT. N over V is molarity. So if I take my V over here and my R and T over there, and these are constants for the reaction, our gas constant, and let's say our temperature is being maintained at a constant temperature as time goes by, and this portion right here, moles per volume, would be synonymous with molarity, we can see that there is a relationship between molarity and pressure. Therefore, you can be monitoring pressure as time goes by and not have to do it in terms of concentration every time. So this is the end of our first learning objective, how you define a rate of reaction in terms of change of concentration of either products or reactants.